This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
All right. Now we get to talk about, I think, the moment you've all been waiting for, right? CFS NHERI. Where you're at UC San Diego, the LH Post shake table. As a mechanical engineer, I love what goes on below the shake table, all the hydraulics and everything. But let's talk about what's going on above the shake table getting constructed there. They're really excited.
Well, we should talk about it below the table for just a minute, though, because this project has been around so long that the LH Post site out at San Diego actually went through an upgrade, right? It was a one-dimensional table, and it is now a 6 degree of freedom table. This particular CFS NHERI project, which is our cold form, that's our shorthand for our cold form steel project, it started pre-pandemic. And it's, I think, in year 7 now of a 3-year project or something like that. So it's been a long journey, and along that journey,
the 3-year mission that's now.
Yes, exactly. We're like the Star Trek guys that got lost.
Yeah.
But it's because of the incredible work of Professor Tara Hutchinson, who we'll talk to, I hope, at another time,
Absolutely,
and many of the other collaborators, but also the industry working hand in hand with NSF to make an enormous project like this happen. So what project is it? We, as a capstone for this effort to really understand the size and performance of taller cold form steel buildings, we have detailed and assembled, and it is now actually on the shake table, a 10-story cold form steel building. The code would limit it to 65 feet. So it is beyond code limits in its height, beyond code limits in its structural system. So we used experimental work from ourselves and other colleagues to develop the actual structural system. So it is really showing us how far we can go with a really lightweight system like this, and really, using that to uncover the resilience and performance of these types of systems. So super excited about just a few months from now, we're sensoring now, we'll begin the white noise tests and really start to understand this creature that we've created out there in San Diego.
Oh, that's awesome. I'm looking now at if we'll put a link to this in the show notes, but there's live video streams from the shake table on the UCSD's Engelkirk Structural Engineering Center website. And it's there, they got a southeast facing one, northwest and southwest, and it is looking good. It's actually raining down there.
Yeah, it's raining there. And even the construction was part of the project. So actually, a full half of the building was full 3D modular construction.
Wow.
All cold form steel. So it doesn't have the usual hot rolled steel perimeter frame. So that was a collaboration and additional funding to actually. We designed a sort of stick built, and then we redesigned it for panelized and modular. So every aspect of the building has really been a learning curve for the research team, but for industry as well. We're really utilizing it to make sure everybody is maximizing what we're learning from that effort.
Actually, what we can do, since this is going to be on YouTube as well, so those of you who are listening on Spotify or Apple Podcasts or whatever, go over to YouTube, because I'm going to just share my screen here with the actual.
There it is. Yeah. So it's just topped out a couple of weeks ago, 10 stories tall. You can see it's a kind of effectively, it looks like kind of 2 rooms, and you can kind of see what would appear to be sort of a balcony. It's originally designed as a large full-scale hotel/apartment building. This is a slice of that building. Then it's a 10-story slice of what would have been a full footprint building. And so those balconies that are you can see in the video are actually where it cuts through the slice of those rooms. Had to do some redesign so it could it could stand on its own as a 10-story building. And you can kind of see where the modules are. So it's panelized on one side, modular on the other. Obviously, this is a building in which we're testing it with full finish systems. So there's the structural system, the finish systems. There's non-structural in it as well. There's gas lines. They don't have natural gas in them, but and sprinkler systems. That's a huge collaboration that NIST came along and partnered with us on all these non-structural aspects. So it takes a village. You can see banner on the side. You can't see the details of it, but it just goes on and on and on in terms of the logos. This is one of
Yeah,
those
I think there's two
NASCAR
of
sort
them.
of things, like 100
You
logos.
actually topped out one of the
Everybody that's touched steel is part of this building at
That's
this
awesome.
point. Yeah, it's
It
fantastic.
and this is like Tara also worked on the Tallwood project with Xing Pei, and you know she worked on the non-structural systems there as well, and so it's really cool to see you know this you know take a lot of the lessons learned from that 10-story building and put it into a completely different construction method.
Completely. Working with Tara Hutchinson at San Diego on this is it's just a complete game changer in terms of our pace of work and the depth of what we're able to accomplish. And she is also an incredible colleague and networker in terms of bringing in these partners to make this happen. It's a dream come true to be able to build this. When I tested a two-story building, which now looks so small, on the
Right,
shake
that's just
tables at Buffalo
down
and
there.
Nice. Yeah, exactly. I thought that might be the biggest test I ever do in my career. This surely will be the biggest test I ever do in my career, but I don't know, maybe not, right?
Maybe not, right?
Yeah,
I
exactly,
mean,
right. So
they're only limited by the FAA out there at
that's
UCSD.
right.
Who
But
knows?
wouldn't be possible without Tara. It's amazing.
Yeah,
And
this doesn't even close to top out the load capacity of the shake table there either.
right, but that's primarily because we're lightweight, right? So
Right.
a 10-story cold form steel building weighs, significantly less than tall wood, weighs significantly less than, a 10-story RC or structural steel system. So the payload of the table can take more because mass is really what drives, what you can do.
Yeah. Yeah. So if you're, out there listening and drooling over this, put in a proposal for a 20-story version.
Yeah, I mean the Miramar Air Force Base is right there, so there will be a limit at some point where they're going to get cranky, I would assume. But so far, so good.
Yeah, I mean, you can. We were out there for the Tallwood test with NSF and our program officer Joy Pauschke, who's been amazing. But their communications guy and I were up on the top floor videoing F-35s taking off and landing and playing the Top Gun theme in the background.
Yep, absolutely. I hope to see you enjoy on the top of this building here in a few months.
Yeah, yeah, that'll be great. But I don't know what the actual ceiling is, but it's a couple thousand feet or something that you could go up to, which would be really interesting. I don't
Sure.
think it's structurally possible.
Yeah.
Yeah. So what are some of the like exciting either structural or non-structural things that you've talked about the modular versus panelized construction. What are some other elements of this that you're really excited to see in the testing to come the next few months?
Yeah, so absolutely. So one of the things that happens as you go up taller in cold form steel and the gravity loads start to get bigger or whatever is you start to get into bigger member sizes. So particularly for the cold form steel shear walls that make up the primary lateral system up the heart of this building, and the lower floors, they actually use HSS shapes and power actuated fastener steel sheet to provide the lateral system. So it becomes a mixture in the lower floors of some hot rolled structural tubes and cold form steel. So that's a great
Oh,
partnership. You're sort of getting into these kind of hybrid type of structures down in the lower floors. Really interested to see how that performs. As we were developing these systems, we came to learn that the West Coast structural engineers had a very different detailing system for the way forces transfer across the floors vertically, like to use a secondary kind of tie rod system. And the East Coast structural engineers, even in the seismic areas, like to use a kind of direct welded type of connection. So we actually have in the north-south and east-west directions two slightly different details for the multi-story system. And we have the ability to test shaking only in north-south and shaking only in east-west because it came a 6 degree of freedom table. So we can do
right.
white noise and really like look at some of these details. So before we replay the full earthquake motions in their full three-dimensional glory, we can actually do some really specific things to understand how some of these details are affecting things. Interior to one of the rooms is a modular staircase, which goes all the way up top to bottom from CS in Texas. Donated the whole system. It's
Wow.
both functionally how we get up and down in the building.
Yeah.
It's also a part of the experiment.
Is it
So
similar to the system from Tallwood
it
or
is, yeah. It's the same company, CS
okay.
Construction Specialties, that provided that. So they're an incredible partner for NSF and in these situations. And we're again looking at different types of detailing that they use to make those systems be able to drift without throwing a lot of stiffness into the system. They're going to be really interesting this time because our system is pretty flexible. So we'll really test out whether they're sort of drift-ready systems, exactly how they perform when we're shaking. We're going to do fire tests on this building, so it has
Oh,
full
wow.
shaft well. So when we're done testing, they're going to do fire tests. That's with some additional collaborators, including one of my colleagues here at Hopkins, Tomas Cornet, and other friends. Um, and then I mentioned the collaboration with NIST, which has a number of non-structural systems, which we'll be able to take a look at. So, yeah, as a structural engineer, I'm really interested in the overall performance and the load sharing between the designated structural system and all the rest of the building. That's really been the secret sauce of the system behavior for cold form steel, is really understanding that load sharing. And then we've got all these other objectives layered on as well. So, yeah, it's going to be fascinating. And, right now we're just working on the hundreds and hundreds and hundreds of sensor channels to
Oh
figure out
gosh,
exactly
yes.
what we can measure and what we can't, right? So it's that's the thick of the battle right now today.
Yeah, I was trying to find a picture. I think I found one of the underside of those stairs from Tallwood. See if this will work. Screen sharing is paused. Resume. Maybe.
Yeah, I can certainly share some pictures from our building as well, but it's the same system with that drift ready system that
Yeah.
allows
Well,
that
it's
mid-height stair to kind of float, is the idea.
there we go. Yeah. So this is from the underside of the Tallwood stairs. Um, but yeah, it was interesting to see how this whole system can float around, but it just works like normal stairs.
Yeah. And this comes from observations that have happened post-earthquake where damage in staircases is both the greatest damage that we'll often see even at a low magnitude earthquake and the most concerning because it's egress, right?
Yeah.
So you're like, so the stiffness differential between a conventionally detailed stair and a building can be an earthquake problem.
Yes.
And so there are technologies like this, changes in the codes, changes in the way engineers think about these things. Stairs used to just be whatever, design the building, there's a hole, they're going to put stairs in it.
Yeah. Put
And
stairs
now
in.
there's
Yeah.
and a lot of that work has come from NHERI and NHERI to really shed a light on our understanding of this. So, it seems like a small thing, the stairs in a building or whatever, but I think the amount of research that's happened to create more resilient buildings because of these particular programs, you can really see it in a simple detail like stairs.
Yeah, and it gets to the point of we're both from the Midwest, right? So you got the New Madrid fault that is going to go someday, and is not something that a lot of structural engineers have thought about until the past couple of decades. But this is a really poignant piece here to look at of as new construction or retrofits are coming in places like St. Louis, Chicago, Lafayette, where I came from, is hey, incorporating seismically resilient stairs is a key design consideration in these areas, and it doesn't have to be. I mean, this, at least to me, doesn't look like it would be magnitudes more expensive to install in new construction.
Yeah. And I think we should take pride in the fact that we live in a country where scientific lessons learned like that get turned into building codes, which get adopted by states, which increase the resilience of our infrastructure, of our buildings. And for a lot of my earthquake friends who go every time there's an earthquake in the world and they go and do surveys, 9 times out of 10, they're seeing the exact same thing that we already understand and have seen before, but that particular country has lax enforcement of its own building rules or hasn't adopted global rules that we know. And so it takes a lot for us to have a safe infrastructure, a lot of science involved, a lot of policy, a lot of people, building code officials and inspectors. But when we do it right, we all benefit from it amazingly. And so, I'm proud to have been part of that in the NHERI and NHERI train over the last couple decades.
Yeah, exactly. And we won't go into it too much. We don't want to speculate about things, but NHERI's coming up on its whatever is next to the next 10 years, and we're just really all of us are grateful for Joy Pauschke and her support from her for a program officer point of view at the NSF and all the other NSF partners that we've had along the way, and looking forward to even more transformative research. Should NHERI can continue in some way, shape, or form with
Yep.
all the stuff going on. But
Couldn't agree more.
as you point out, it's in every building that we interact with, either out here on the West Coast, in the Midwest. There's hazards everywhere that structural engineers need to design for, and it's really cool to see all these innovative methods that not only mitigate the hazards but are better performing in day to day and also cost perspective as well.
Absolutely. And it's it's a little bit unique, right? All of this wisdom doesn't get turned into a product that gets sold and then everyone says, oh, here's this company that made $1 billion that provides this particular safety for you or whatever. They aren't cars, right? I mean, these are public goods for the most part. And so most of these advances are non-proprietary, and then they're turned into wisdom, and in some cases, prescriptive rules that get passed on to the entire body of practicing engineers and architects that create our buildings for us or whatever. So it's a different process, this path of innovation to safety, than the one that most people think about these days with the path of sort of innovation to commercialization. But it's super important, and our society is really relying on it. And I'm thrilled to get to celebrate it and to participate in it.
Yeah, it's really amazing to see how this is going, and even how the NSF approaches getting things to market. We've got the new Tips and Science director or Tips Directorate that is looking at how we transform research into practice through commercialization, but doing it in an open way. It's really exciting to see where things are going.
Absolutely.
Where can people follow along with your research as we go and keep on the train with CFS, NHERI, and all the things that you're up to?
You bet, right? I mean, so go to the World Wide Web instead of ChatGPT and get the latest information. CFS10.ucsd.edu has everything about the latest testing. That's definitely where I would send people. CFSEI is the Cold Formed Steel Engineering Institute, cfsei.org. I'm a past president of that organization and a big fan, and they're a great disseminator of everything a person needs to know on cold formed steel. And there are many more, but those are two. If you want to do research or you want to sort of get anywhere on the ground floor of understanding cold formed steel, that'd be number one and number two for me.
And it's been a great chatting with you. Looking forward to seeing you in person in a couple months or so, and keep up the great work.
Yeah. Thanks so much.
Take care.
Thanks for listening to today's episode of Design Safe Radio. Be sure to like and subscribe on whatever platform you happen to be listening to this on. It really helps people find our show. Thanks to our amazing sponsors, the National Science Foundation and the NHERI Network Coordination Office, which is award number 2129782. Big thank you to Marty LaChance, our guest booker and topic researcher extraordinaire, and Raquel Ruiz, who is our video and audio editor. I'm your host and NHERI Facility Scheduling and Operations Coordinator, Dan Zahner. We'll see you in the next episode. Until then, stay resilient.